round up immune system. We will start problem-based learning on Wednesday, where we'll be in small groups doing a case study type thing. I'll assign groups, trying to get some good group dynamics. And hopefully maybe haven't worked together much before. I don't know you that well, but just trying to get some good group dynamics. That's coming, that'll be for 2 days. So the way that'll work, I'll describe a little more on Wednesday, but on Wednesday you'll start the case, and at the end of Wednesday, the aim, the goal, is that there's a lot of things that you have a lot of questions about, that you don't understand. So you go home, and for the next several days, you do at-home research, literary research. I don't know the case yet, so I don't know what it could be, but about some sort of immune diseases or immune system, how it works, something that you haven't come across yet, that you need to study a little further. So your whole group will decide what you're going to study. Maybe you divvy it up. This is a group decision. I have no say so on this. And the group may say, well, you go research this, you go research this, and you go research this. And then when we come back on Monday, the first 10 minutes or so, 15 minutes, we'll talk about what we learned. Okay? Or your group might decide, let's all of us research these subjects. And then we'll come back Monday and kind of bounce ideas off each other. So that's a group decision. You guys get to decide that on Wednesday. Okay, but we'll talk about all this a little bit more when it comes. So that's, and then next Wednesday, remember we moved respiratory system up to switch flip-flop it with the exam. In case I didn't say this, respiratory system will not be on the exam. Respiratory system is going to be saved for exam 3. Okay. Instead of splitting it in half, which is kind of weird to do. So that means after today, the material we will have covered for the exam, you have what? Almost, not quite, but almost 2 weeks of study time with the material we have covered. Okay? So this should also be helpful for everybody. Okay, any questions, comments, administrative stuff? I think I've covered all the, don't have any other technical stuff going on. Connect. Oh, Connect, that means your due dates are going to be moved around. Did I already do it? I think I meant to. I don't know if I've already done it. I'll go check. That means your respiratory system is going to get moved from the 17th up to the 12th. Okay, so keep an eye on that because that will change. I meant to have already done it, but I might need to go check to make sure I did. Okay, so that's okay. You have a break from Connect right now for next week or so. You don't have any of those assignments. You don't have anything due Wednesday. You don't have anything due Monday. And then you'll have something due Wednesday, respiratory system. And then those quizzes, those, I think there's 5, they're real short, right? They're due on the 17th, so that's coming up. Most of you have already finished, but those of you that might need to polish those up, those are due on the 17th, that first chunk of them, so be sure you're getting those in. So we have a little bit of breaks coming up with Connect for the next couple weeks. Okay, that's enough for announcements. Let's finish up the chapter. Let's start by make sure we know where we're at. We've done this chapter. This will have been the 3rd day, right? This is unique. We don't ever spend this long on a chapter. We started with lymphatic system, the lymph, where it comes from, the vessels, the lymph capillaries, how they're similar or different to blood capillaries. Talked about collecting ducts, all that sort of stuff, and circulating lymph nodes, thymus, all that. Okay, that was the first go around. Second go around was the innate immune system, right? Innate immune system, inflammation, complement, the cells that do this. Talked about what do we talk about? Natural killer cells and macrophages that do phagocytosis. Is all ringing a bell? And so that leads today to do the adaptive immune system for acquired. Okay, so that's where we have left off, and we're continuing on. Okay, so we're going to spend the rest of today talking about 2 types of cells. That would be our, which ones?
T cells.
Yes, T cells and B cells. So up to now, we've been lumping them together as lymphocytes. Now we need to talk about them a little more specifically. So up to now, we have looked at how they look microscopically. How should I draw the nucleus in a lymphocyte? Any thoughts? Any thoughts? What type of nucleus does a lymphocyte have? Okay.
It's a thicker solid.
Yeah, sorry.
It takes up the majority.
I'm still having asthma problems, so you gotta give me a sec here. Yeah, that's why I was like, that one over there. This is the real thick nucleus that takes up almost the entire cell. So something like this, and it's real dark blue, right? The staining's a blue color. So the nucleus will be a real dark all in here, and it takes up almost the entire area of the cell, a volume of the cell. Like is, and that's really kind of all we described them to this point. So now we need to get more specifically. When you're looking at this, can you tell which one's a T cell, which one's a B cell? In the microscope? No, you're not going to be able to tell. This is stuff that is molecular. You have the molecules are different, but you couldn't tell in a microscope. Okay, so let's start by describing these two cell populations, and I want to do a little bit of a chart here. T cells, and we'll go down here, B cell. First, let's start, where are they born? Where are T cells born?
Red bone marrow.
Good. Red bone marrow. Where are B cells born?
Red bone marrow.
Same place, red bone marrow. Okay, we looked at red bone marrow. You do this in your head on whatever day that was. Wednesday. I had some figures up here. I was asking the groups to analyze some of these figures. I think the first one we looked at was the red bone marrow. You see that in your head? That's what we're talking about. That's where these cells are being born from the hematopoietic stem cells. But they're not functional when they're born. They have to mature and then get even activated to be able to do a job, right? So the first thing they have to do is mature. Where do these different cells mature?
And protein, like binding to protein.
This is some basic, hopefully. This is repeat chromosomes. Okay, so it's easy to remember this. T cell, T for thymus, and B. You can think of it as B for bone marrow. That's originally not where the name came from, but it doesn't matter. Okay, B cell for bone marrow. Okay, all right, we need another column on our chart. Okay, just because these cells become mature, they need to pass a test to prove that they're mature. Okay, so we're going to give them a test. Okay. The way that these cells can fail, how do they fail this test of whether they're worthy of being part of the immune system? What is going to be something that makes them fail? Yes, if they we're going to call it bind self. Okay. If this cell, the T cells, and we're talking about T cell right here. Sorry, okay. We're talking about T cell. It binds to anything that identifies you as self. We need to eliminate that cell, right? That's a problem. You do not want your immune system recognizing yourself. That's autoimmune disease. That's what happens in those diseases. Okay? Your immune system starts binding to your own antigens and starts attacking them. Okay? So that's one way to fail the test of whether they're worthy of continuing on in the body. Another way are these cells. How can these cells fail this test? they bind the wrong thing, or they bind,
Each other.
yeah, I guess. That's not what I'm looking for, but that would be a problem too. That would be binding the wrong thing, if they're binding to each other. They don't bind. Okay? They don't bind at all, which is common, okay? Either they bind to self, or they do not bind at all, okay? This, I'm going to add another term. They do not bind. Specifically, we're referring to MHC. We have not gone through MHC yet. I'm going to do that next. MHC stands for, since we haven't gone over it, you write it out. Major, I think you should have seen this before in your Connect. Histo, ability complex. Let's let go that there's more than just one thing going on here. It's kind of a complex, several things. Okay, that's what MHC stands for. So if these T cells fail this test, they need to be removed. That process of removing the cells is called negative selection. Right? What happens to, what's the name of the process if cells are asked to be eliminated? The cells go through the process of apoptosis. Okay? I think have we gone over this word before? How it has a different pronunciation. Have you ever seen this word before? Okay, this word apoptosis. You're going to see this pronounced three ways. I say apoptosis. It's just the way my training went. And I skip the second P. Apoptosis. And you're going to hear apoptosis. It's all the same word. It's just different scientists across the country pronounce it differently. And there's debate among linguists how it should be said, and nobody's agreed. So you're going to hear all three ways of the pronunciation. Okay? It's all the same process. So how do we define this apoptosis process? This is a normal thing for cells to die. So it's normal, so we're going to call it programmed. Like the instructions for cell death. As opposed to necrosis. Necrosis is cell death when something's getting sickly. Is telling a cell, we need to get rid of you. We need you not to be around. Okay, it's a nice way of saying, please kill yourself. Okay, that's apoptosis. Okay, but you can see why this is a problem. I mean, this is if it's not doing its job, it needs to be eliminated. You can imagine like an employee. An employee not doing the job correctly puts the, say you're in a clinic working, you're putting those patients at health at risk. Okay, so you need to train the employee or remove the employee. Okay, in health, there's no training program put in place. They are limited. Okay. Okay. So that's negative selection. So to pass the test is just the opposite, right? The cells will recognize MHC complex, and it will not bind self-antigen. Okay. That process is just the opposite here. That's called positive selection. So if a cell in now the bone marrow, well, the T cells. Let's stick with T cells. The cells in the thymus, if the thymus finds a good one, it's like, hey, let's multiply that one. That cell undergoes rapid mitosis. Okay, so now we have positive selection because we found a winner. Okay, and we divide that cell, multiply it by mitosis. That is called clonal expansion. And you get a second one. now we have several, thousand, hundred, I don't know how many, thousand, probably 2,000 cells that are doing what they're supposed to. They're coming from one, single cell. Alright? Okay. So this process, is true for T cells and B cells. It's not, it's in a different location, right? T cells, this process is happening in the thymus. B cells is happening in the bone marrow, okay? Okay, MHC. So this test of MHC, what type of cell is giving the test of do you find MHC? Okay, let's go to the thymus figure. Okay, pull the thymus figure up in your brain. Got it? What do you see? Reticular cells. You see a cortex. You see a medulla. Cap. Some descriptions you gave on this figure was that the cortex looked more compact, or more cells in there than the medulla. So you have the figure in your head. Okay? So what cells are getting the test? Adrian's whispering it over here. Okay, the reticular cells are giving the test. Okay, so remember in this figure, there was reticular cells over here and it had branching out arms, kind of like this, contacting all those T cells. And they were over on the medulla side as well. You identified the reticular cells, and we didn't really talk about their function at the time. But one of the things is they present MHC to T cells to see whether they're going to find it. They also present self-antigens to see if they're going to react. Okay? Okay, so this is T cell kind of maturation in a nutshell. Okay, if the cell goes through positive selection, so it's cool, it's good to go. This cell is now allowed to leave into circulation. At this point, it is called naive. Okay? Naive. It's not active yet. It's not doing anything. At this point, it's kind of going around the body scanning, looking for antigen. It's looking for foreign antigen. Okay? Whatever that might be, a virus, a bacteria, pollen. Okay? Pollen is considered a foreign antigen. Some immune systems react more to pollen than others. That's allergies. Okay, but they're naive. So right now they're not active yet. We need to talk about activation of these cells. Okay, what do you think the pass rate of these cells? How many pass? All of them, some of them, half of them? Did you come across this number in your meetings?
I think it was like
You should have, because I know it's there.
2 or 4%.
Yeah,
somewhere
somewhere
around.
between 2 and 5%. That pass. If I had a pass rate of 2 to 5% in this class, pretty sure I wouldn't have a job anymore. That is not a very high pass rate. You can see 95 to 98% of cells that are born are asked to eliminate themselves. They are not born correctly. So look at how important that process of negative selection has to be. Okay? Because almost most of them don't work. We have to get rid of all of them. Only a small percent recognize foreign and will bind the MHC properly. Okay, so that summarizes that chart. Let's get into cellular immunity in more detail, talking about the T cells. We're going to start with T cells. Mostly. I earned my doctorate studying T cells. Okay. let's look at T cells. The first thing about T cells, okay? So as we go along in immunology, you learn more and more categories of cells. So we started with lymphocyte, then we went to B cells and T cells, and now we're gonna tease those out into even more categories. Okay, starting with T cells. Some T cells are called cytotoxic. Okay? Another way to refer to those cells, you might hear T8 or CD8 positive, but really you're going to hear CD8. Is another way to refer to cytotoxic T cells. These carry out attack on the enemy cells directly. They find a cell that is infected by bacteria or virus and kill that cell. Kind of like a natural killer cell. So it's a separate population, but a similar process. Okay, we saw this video, didn't we? Yeah, we did. Natural killer cell. Remember this? Mm-hmm. Attacks the cell, releases weapons. Okay, similar process. This is not a natural killer cell. It's a different cell, but does it similarly to those NK cells, cytotoxic. Some T cells are helper cells. Okay. You may see these referred to as CD4. These are different, these are more markers on cell surface. Okay? CD8 and CD4. There are hundreds of markers out there. Okay? These are just a couple of them. Helper cells help promote other cells. They don't attack directly. They kind of send out orders. They're like, okay, macrophages, you need to come do some job over here. Okay, B cells, we need some more antibodies. Okay, natural killer cells, come do your job. So they kind of mark out orders. But then the cells don't kill the cell. Okay, can you see the difference? There, that's helper cells. Regulatory cells, Tregs. Okay? With the immune system, you don't want it to get out of control. Okay? If the immune system gets out of control, it makes you sick. Okay, it causes all sorts of issues. So when you're combating a cold, you need to fight the cold, and once the cold's gone, you need to stop. Okay? The Tregs have a lot of role in maintaining that. Okay, these are a fairly new population as far as science goes. So there's a lot of work to figure out regulatory Tregs. Last category is memory cells. If you got a cold this week, okay, a subset of your T cells will be saved for when you get that cold. Now, a lot of you are going to say, wait a minute, if I have memory cells, then why do I get a cold twice? Why does that happen? Virus changes, okay? So it's a different virus that you get a couple months from now, yeah. So every time you get a cold, it's a different virus. So yes, you get memory cells, so you don't get that virus again specifically, but the virus mutates quickly. Okay? Okay, so these descend from both these populations to be ready to combat. Okay? Okay, let's look at CD8 and CD4 is now activated. Okay, how they get up and running. Let's draw this out. Okay, we have a cell. Okay, let's get my drawing down in my head. We have a cell. Okay, so let's draw. I'm going to draw a cell membrane kind of like this. Right, this is a giant cell. We're going to get infected by some kind of virus. Okay, so that's supposed to be some sort of virus. Is going to get into this cell in here. Usually, most viruses fit their genome into the whole virus doesn't go in, just the DNA goes in. But we'll draw it like this. The virus goes in. Oh, I'm not trying to. All right, virus goes in. Okay. What the cell will do with this virus, there's a couple of options. proteasome. So proteasome is always drawn like these spirals. I don't know why. I don't know if it actually looks like that. It might, I'm not sure. I remember. This is a proteasome. Okay? So the virus gets taken through here into pieces. Okay? All right. In this cell, what's going to happen with these pieces, okay, over here, we're going to have another structure, this is their nucleus. Whoops. Okay. Which organelle is kind of attached to our nucleus? Kind of pancakes looking thing? A little bit like pancakes-ish. Remember, which organelle is attached to the nucleus? Yes, thank you, that one. Okay, so I drew it kind of big, just for illustration points purposes. But what's attached to the nucleus is the endoplasmic reticulum. Reticulum, thank you. Specifically the rough. Okay, the smooth ER can be away from the nucleus. But this is the rough endoplasmic reticulum. Okay, so what happens is these viral particles, okay, sorry, I skipped a step. Let's go over here of what we're going to find in plasmic reticulum, specifically the rough. Okay, so what's the job of the rough endoplasmic reticulum? Okay, so it has ribosomes. So that's what makes it rough, right? Is that on here we could put these dotted things. I can do it throughout, right? All over. Things over here. And these are the ribosomes. Okay? So what's the job of the ribosome? Protein synthesis. So what's the job of the ER? Okay, so you're on the right concept here. The ribosome is protein synthesis, protein modification. Okay, so when the protein needs to be folded, or if a protein needs to have a sugar, a glycosylated, a glycose group added, or it's a glycolipid, okay, alteration. So protein modification is the job of the ER. Okay, so one of the proteins I'm trying to get to is the MHC complex. So in here, I'm going to draw MHC like this. That's a complex right there. That's everything put together. And that's an illustration. MHC complex. Okay, the next way the ER works is that you get buds off ER. Remember this? So the ends will kind of start pinching off. And then you start getting these vesicles, right? These are transport vesicles, okay? These transport vesicles are transporting to the cell membrane. If we are transporting to stay within the cell, where might this go? The Golgi. Also has to do with transport, okay? But anyway, we are getting transport to the cell membrane. So that's what's going to happen here with our MHC. Okay? Make sure, yep, okay. So we get a vesicle here that has our MHC in here, okay? This vesicle also picked up these protein, viral parts, also ended up in the ER. Okay. When they are in the ER, they are bound, they are given to, bound, to the MHC. Okay, now I just said viral particles get to the ER and they get down to the MHC. That's a complicated process. We're not gonna go through all that, but I want you to realize the concept of anything in the cell. If you say it goes there or gets there, there's a whole process for how that works, how that's accomplished. Okay? It's not like the viral particles just on their own decide, hey, let's go over there. Okay, there's a cell process that controls this. Okay. Anyway, what's important for us, the viral particles end up in the ER, the viral particles bind to the MHC here, and then we get a vesicle that buds off. Now this vesicle can transport, move to the membrane. I'm actually going to add a color so you can see how this works. Okay, and we do the process of how do we get a large thing from in the cell to out of the cell? What's that process called? Good. This is exocytosis. Okay, so the process of exocytosis right up against the membrane, like so. Okay, these two are the same. I ran out of room, so they look different sides, but they're supposed to be the same. They come up right against the cell membrane, and then they open up the membrane here. This doesn't give a pore into the cell. It gives a pore into the vesicle. Okay? Well, now that we have the MHC, like so, you can see how this is now kind of exposed to the outside. And actually what these do is they end up, how many drops is this? Kind of like this. Cutting out. I mean, it starts opening more and more and more so this vesicle is completely fused to the outside. So you can see how this MHC will eventually exposing on the outside of the cell. Okay? There are several, I don't know, 100 of these. I'm drawing one to illustrate the concept, the process. But there's many, many of these in this vesicle doing this. Right? So now we have this cell, C, with this viral piece exposed to the outside of the cell. Alright? Okay, so let's add some detail. I keep saying cell here. Okay? Oh, I haven't mentioned. There's more than one type of MHC. This is easy. MHC1 and MHC2. Okay? We got 1 and 2. This process right here is describing MHC1. MHC1. Okay? If I am referring to MHC1, what type of cell is this? Any thoughts? This is all nucleated cells. So, your liver, your tongue, your muscles, your heart, all of them, they're all the nucleated cells. So that means what does not have MHC? The cells in your body do not have a nucleus. Red blood cells. Red blood cells don't have nucleus. Remember that whole process of erythropoiesis? A few times, right? Part of that process, the cell starts with a nucleus, but then when it's ready to actually enter circulation and be active, it spits the nucleus out and degrades the organelles. Trying to remember this process? So, now, this is why blood transfusions are possible. Okay, we don't have MHCs. Organ transplants. Organ transplants are more tricky, right? We hear about this all the time. Maybe you've experienced it personally, family, something, or just heard about it in the media. Organ transplants are much more tricky to get a match. MHCs, even though we all have MHC on our cells, our MHCs are all a little different. And if they don't match, immune systems attack. Okay? So this is exactly why organ transplants are more challenging. Right here. Whereas red blood cells don't have them. That's why we talk about the other markers, the ABO. Those are the ones that cause issues with mismatches. Right? Okay, MHC1, all nucleated cells, virus, cell. Okay, I think that's MHC1. Let's draw MHC2. And how that process works. Oh, I wonder if you do this on your own? No. Yeah. MHC2?
Oh.
Arsenic? Anybody want a marker? Anybody want a marker? No, not yet, no. Okay, let's go together then. Okay, so we have a cell here. Okay, so let's start with, over there, it's all nucleated cells. Which cells have MHC2? This is only a subset. Which ones have it? So which ones? Leukocytes really these white blood cells. That's a big category. Okay, so that's the category. So these are, oh, how much detail do I want to give you?
Antigen presenting cell.
All right. The word antigen, excuse me, presenting cell. Let me describe a little bit of what's going on with this term. Obviously, there's more to the story. This over here is presenting the antigen. Okay, you have viral parts, viral antigens. They're being presented. So this would be considered antigen presentation. Be considered an antigen presenting cell. So what we want to say over here, to be more precise with our language, is call it a professional antigen presenting cell. It's kind of their job. It's what they do. It's this group of cells. Okay? So there are 3 types of cells that do this. They are, dang, I thought we were going to go 1, 2, 3, bam, and be done. B cells are a professional antigen presenting cell. Macrophages are professional cells. And our last group is called a dendritic cell. We're not going to have time to go through dendritic cells. We're running out of time. They're cool cells that really part of the immune system, but we're going to run out of time. I'm going to turn this one off because we keep doing weird flash. Is that cool? Okay, MHC2. So this cell here is either a B cell, macrophage, or dendritic cell. And we're talking about MHC2. Okay? This time, we have a pathogen that's extracellular. So over here, our pathogen went intracellular. Over here, we need a pathogen extracellular. So particularly bacteria. Okay, I'm going to draw some bacillus cells here. Okay? So this isn't strictly viral and strictly bacteria. What the word you use is intracellular and extracellular. So intracellular, many bacteria say extracellular. And that's not 100% true all the time. So we need to say extracellular pathogen. Okay. So these cells order to respond to cellular pathogen, need to get it inside. So that process of bringing pathogen inside is endocytosis. We're gonna do the opposite over there, okay? A vesicle, okay, is going to open up here, so the vesicle fuses over here, and opens up on the membrane, and kind of encircles these bacteria, okay? So now let's have a vesicle with these three cells in here. Okay? All right, we still have, this cell still has a nucleus. And we still have an ER over here. Rough ER. Smooth ER too, but rough ER is what we're talking about. The ribosomes. Okay? The MHC2 is still made in here. I'm going to draw it a little different so that we know we're talking about MHC2 and use more of a square shape. Okay, 2, that's just clarifying between 1 and 2, because it's a different type, a different protein complex. Okay, so the difference is here. This is kind of where the two processes all different. So now we have, from the ER, we get a bud here that has NHC2 in here. What happens is these two vesicles fuse. Okay? So that we get one kind of giant one. What is also present in this vesicle is a bunch of enzymes. Change color so it doesn't look like a rat. In here, we have a bunch of, these are proteolytic enzymes. Or you can also call them degradative. Okay, just a term that means it breaks things down. This vesicle fuses with this vesicle. You can see how these enzymes will be degrading these bacteria. Okay, that's happening in here, in this big one. Okay, so then now we go from bacterial cells down to bacterial pieces, antigens. Okay, now these antigens, now that they're broken down by the enzymes, can bind to or MHC2. And what's the last step I need to draw this process?
Exocytosis.
Exocytosis will get this bacterial piece exposed to the outside.
So what does that mean for your phagocytes or your macrophages? They won't attack that particular cell because that cell is the one that's exposed in the body.
They will eventually. Once the presentation
Will always be destroyed.
Wait. This one, you're right. This one will not. This one will.
Yeah.
Sorry. Yes, this one will. The intracellular ones will be targeted.
So how does the body react? It just finds those antigens in the extracellular tissue.
Yes. So this is how the body is going to deal with battle extracellular pathogens. Okay. So the first thing we have to do is make the body aware that there's an extracellular pathogen in our midst, okay? So we're talking, so these going to come respond to this or this. Who's going to come say, aha, there's something there?
T-cells.
What cell is that?
Or B-cells.
T cells and B cells. Okay? It's not as much B cells, but it's particularly the T cells. Okay? The T cells, which we're going to talk about next, is how the T cells come in and recognize it. So T come recognize this, and they're gonna recognize MHC2. So they're gonna know extracellular pathogen. So they're gonna know this is the kind of battle we need to do, okay? Or if they say MHC1, a different kind of battle. We need to deal with this.
They're looking for the cells that have been.
Yes, it's a different type of response to deal with a different type of pathogen. Okay? Okay? So, I said we're gonna talk to T cells. We're gonna do B cells later. We're gonna stick with T cells right now. So T cell, so now we need to have another cell come over here and recognize this and have a reaction. Okay? Okay.
And that's
that-
always gonna be a T cell?
Majority. I think B cells will do this a little bit. But I can't think of any other cell that would. Mostly T cells. I think B cells can respond to MHC2. No, I'm gonna stick with T cells. Let me know that B cells do this. T cells are responding to the MHC, okay? Okay, the slide before this, what was the slide before this?
The different categories of cells.
Okay, good. The different categories, right? Cytotoxic T cells, helper T regs, that one, okay? So, the cells are going to respond to the MHC1 or the MHC2. The MHC1, the type of T cell we're referring to here, you know? We don't know. CD8, okay? Cytotoxic T cells are the T cells that will respond to MHC1. CD4s, the T helper T cells respond to this one over here. Right? So, when I first started studying immunology, I couldn't get down which was which. I couldn't remember one with 4, 2 with 8, 1 with 8, what, I just couldn't. So I'm gonna tell you my trick. I don't know if it'll work for you. But when I was studying this, I was 24, and my sister was 18. That's stuck with me now. I won't tell you how long. However long it's been since I've been studying this. Some years. Okay, 24 and 18. Those numbers just stuck with me. So associate 24 and 18 with something. It worked for me. I was 24, my sister was 18. So that's how, till this day, I can remember 2 with 4 and 1 with 8. Okay? Okay. 24 and 18, antigen presentation. We got it here 11:45.
So are CD4 helper cells?
Yes, yes,
Okay.
those are the helper cells. Okay, I was gonna do an activity next, but I have 6, 12, 18. I have about 20 slides here, and we've done 3. So we're gonna have to skip this was the important stuff. That's why I took time on it. So we're gonna skip the next activity. Let me tell you what the next activity was gonna be, so maybe you can do it on your own time as a little bit of. Do you need an activity? I got you right here. You need a- Got y'all? All right, we can skip the activity. I'm just worried if I talk too much that I'll lose your attention. What is attention span nowadays? 5 minutes, 2 minutes, something like that? 6 minutes, 8 minutes, something like that? See, I gotta make sure I break it up. We have to have small discussion and then like, let's stretch, and then, and then we can talk about it again. Oh, so we got my slide over then. Okay, the little activity I was gonna have to do, mostly just to break up, that I'm not talking too much. This figure comes out of your book, and I actually don't care for it. So what I was gonna do is ask you, you all be the editor of the book. Tell the illustrator that I don't like this figure. Make it better. Okay, we were gonna spend 5-10 minutes on how we can make this figure better. But we're running out of time. So when you look at this figure in the book, keep that in mind. I don't care for it. The reason, and I'll tell you why I don't care for it, I think it's too general, too vague. So if it were me, we need to add much more detail to make this useful. I think it's so vague, it's not so useful, okay? So look that over and see what I mean and think about through what am I trying to get at. Okay, now we need to get into, we did the MHC side of things, now we need to get to the T cell side of things. How do they respond to that T cell activation? Okay, this slide is just a summary of everything I've just said. Okay, the T cytotoxic T cells respond to MHC1, and the helper cells respond to MHC2. And here's a table of everything we've already said that came out of your book. Okay, so this is just a summary slide that was going on about antigen presentation. Okay, T cell activation. Okay. I don't know how to do this. Okay, this slide is also a summary, okay, of what the T cell is going to do. If the T cell comes and recognizes that MHC, the first thing that's going to happen is called clonal selection. Okay, so how many types of T cells do we identify? Okay, I don't know how to word this. So there are hundreds, maybe thousands and thousands of antigens out there, right, of pathogens and pollen, other things to allergens. Body has thousands and thousands of types of T helper cells and cytotoxic cells. They all respond to thousands of different antigens. Okay? So once that MHC presents that viral or bacterial antigen, there's only a certain type of T cell that is going to match it and respond to it. So once the body finds the match, we're like, oh, we need more of that cell. And we need to multiply them, right? So that's the stimulation and clonal selection, and then that cell undergoes repeated mitosis. Okay, it's not all the T cells will respond to that antigen. There's only a small subset that will recognize it. So your body needs more of those. So multiply them. Okay? By doing that, you get a clone of identical T cells. We're not getting as technical as epitope. Have we described epitope in here?
No.
Yeah, the book does. So, say you have a protein, right? Protein has 3 dimensions to it. A antibody can recognize maybe different parts of that protein in different sections. That part is the epitope. The antigen could be the whole thing, but the actual recognition might be just a small section of that. That's an epitope. Okay? All right, so we find T cells that recognize a certain epitope, multiply them. Some of them are going to go do the effects, and some of them are going to go to be memory stuff. And let me show you a picture. Okay? I was going to draw something, but let's go straight out of here. Okay, I want to show you, I don't want you to memorize this. I'm trying to illustrate a concept here. This is a T cell receptor. Okay? A T cell receptor has many parts to it. This is what recognizes the MHC complex. Now, this is what gives each T cell its uniqueness, because these are variable. So this is a protein, right? This isn't just a drawing picture, but this is a protein. So these proteins can be made differently. Every single one of them can be made a little bit different. That's how they recognize different antigens. Okay? All right, so this T cell receptor has all these different chains. They're named after Greek letters. Alpha, beta, epsilon, delta, zeta, another epsilon. Doesn't matter. They all have names, they have all functions. But I wanted to show you the concept of a T cell receptor is more than just a simple AC. Okay? Okay. So this picture does come out of your book. And this is describing the process. Okay? We have the antigen presenting cell, presents out. The T cell is responding. The way it responds is it makes some cells that are going to go to work, go to do the battle. Some become memory cells and they're going to be stored for later. Okay? The way the T cells go to work, kind they are. Okay? If this is, I already said this, actually. This is just an illustration of what I've already said. Helper T cells, they're the generals, right? Barking out orders. Here's their orders. Green dots, green dots, and yellow dots. Okay? You can lump those together in the term here. Cytokines. That's what T helper cells produce. Are these molecules called cytokines. And these are the ones that are barking out the orders. They're telling macrophages, all right, start doing phagocytosis. Okay? B cells, okay, start making more antibodies. T cells, okay, go attack the infected cells. Okay? So the cytokines are what give out, carry out the orders of the cells. Okay. Let's go to B cells. How do B cells work different in T cells? So, all right, B cells. This type of immunity is referred to humoral. Where do you think that word humoral comes from? Humoral. Don't know. Must be you. I guess it'd be humorous, meaning bow barrel. I'm not sure. But what it's referring to is antibodies. Okay? Anytime you see the word humoral immunity, it's referring to antibodies being made. Antibodies come from B cells. They are responsible for making those proteins. And we're going to look at how antibodies accomplish. We're going to look at how antibodies accomplish immunity here. Okay, first of all, though, the activation is similar in a B cell. Okay? We're not talking MHC, though. We're talking antigen, this green here. See this green? The antibody that's on the surface, and that activates the B cell. Okay? So it's a little bit different that we're not talking about MHC here with the antibodies.
So does the B cell and B cell does it still make the image?
Yes, it'll internalize this and then on MHC2. Yeah, it'll internalize it. Okay? because that's number 2, antigen presentation. The B cells presenting to a T cell here. Okay? Okay, but same thing, the B cell gets selected for clonal expansion, so we get more of them. Difference here, some of them are going to make antibodies, and some of them make T cells. Whereas before we got helper cells and cytotoxic T cells in the T cell story, here we have production of more antibodies. Okay, so we need to look at how the antibodies accomplish killing a pathogen. All right, there's 4 ways. Sorry. Before we get there, we have to look at what the antibody looks like. We've talked about this with the blood. We talked about that in the plasma are globulin proteins. This is what we're talking about here. So we covered them a little bit. So let me just show you the picture. Skip the words. Okay, so this is what an antibody monomer, meaning one structure, looks like. Okay, it's got 4 parts to it, 4 separate chains. Are smaller, so they're called light chains, the purple and the yellow here. And then 2 of them are larger, so they're referred to as the heavy chain. And it has to do with weight. That's where those words came from. Light chains and heavy chains. Each of these protein chains has different regions. Okay? The end here is variable. So this is the variable region. These here in the purple and the green don't change. Okay, it's just naming the proteins. I know it's silly to name all these parts, but it's really important if you continue with studying immunology about how you get variability. Right? The genome is what's making these. The gene in the DNA makes the protein. Well, the gene has to be set up a certain way to allow all this to be variable, and this not. Pretty unique setup, the way DNA put together for this. Okay? Okay, let's look at the attack. That's really what I wanted to get to. So 4 chains, constant, variable. We talked about these a little bit too, huh? Blood. For the ABO stuff, A antigen, or A antibodies, B antibodies, all that stuff. Okay, let's look at the attack. This is what we're most really interested in with antibodies. There's 4 mechanisms. They're called neutralization, complement fixation, agglutination, and precipitation. So neutralization. I'm going to show you pictures of all this here in a second. Okay? If a bacteria has a lipopolysaccharide on the end, the lipopolysaccharide is what your cells don't like, makes them sick. So if the antibody comes and blocks it, well then you're not going to feel so bad. Okay? And that kind of makes you feel better, and then other parts of your immune system are going to come and actually kill the cell. Okay? But antibodies mask that can make you not feel so hot. Complement. We looked at complement last week on how all those proteins come together to accomplish the MAC. What's MAC? The MAC attack. Membrane attack complex. Right? With all those proteins that kind of hole punch the cell, the pathogen, so that you can get fibers inside to kill it. Complement. But antibodies can start that. Remember that? Remember the picture where it showed an antibody that had all these arms coming off of it, and it comes and docks on the bacterial cell, and that caused a sequence of reactions. Body starting that. That's called complement fixation. Okay? Agglutination. If you get an antibody, we looked at agglutination as a bad thing, and what the ABO. If you have a mismatch, if you have a person with B blood and you give them a transfusion of A blood, it's a bad thing because the antibodies are going to agglutinate the antigen. This, in this context, is a good thing because of what we're agglutinating. the pathogen. If you agglutinate the pathogen, you immobilize it. So it can't do its other duties. Right? It can't multiply. It can't spread. It can't infect. It can't get its proteins out there. Okay? Agglutination in this context would be a good thing for antibodies to do. Okay? Precipitation. Sometimes antigens are released from the pathogen. Right? Like with the polysaccharide as an example. Okay, the pathogen, for one reason or another, in certain processes, the antigen gets in your body, the cell. Antibodies can go find that antigen and kind of hold on to it. Okay, so other things come and clear it. So antibodies don't ever clear the thing, they bind it. That binding causes something else to come, or degrade it or whatever. Okay, so antibodies don't kill directly; they bind to all sorts of different stuff going on. Okay. All right, one last thing, and then we can go. Well, this is a picture of agglutination. Okay, we looked at it with the red blood cells. Oh, this was the bad thing. Now it's a good thing. That's the whole point, is agglutinating pathogens. Okay, the last thing is this table. And I know it's small, but you have it in a book. So just study over. This is a very nice table that compares and contrasts humoral immunity, which is antibodies and B cells, immunity, which is a few things, right? The cytotoxics and the helper T cells over on this side. It describes everything I just talked about today in a table format. So it's a good summary of these processes. Okay. It's a good way to test yourself if you're kind of starting to understand all this stuff. Okay. All right, that's all I got for today. Go.